Hello everyone. Okay, in this impulse momentum principle, which is the most important principle of fluid mechanics, right? We'll list out all the three important principles and then how to use this principle for practical problems. Even that also, I think we'll be discussing in this session. Okay. Okay, basic principles of fluid mechanics. There are three of them. One, two, three. Uh, Two of them already we have studied, and this time here we are going to study about impulse momentum principle. Anyway, what is the first principle? It is a continuity equation. Continuity equation for practical application. The format is the discharge equal to Q equal to A1 V1 equal to A2 V2. Obviously, when we say this, if you have a flow, something like that, you have to consider a section 1 somewhere on the flow, and then there is section 2 somewhere in the flow, right? The flow is occurring maybe in the pipe, let us say, or even open channel flow is fine. So at point 1, what is the cross-sectional area of the flow? If it is a pipe, it is easy to calculate, right? Cross-sectional area of the flow, and then what is the velocity at point 1? So that will be A1 V1. Similarly, over here, if you have cross-sectional area as A2 and velocity as V2, then the discharge cannot disappear or cannot add, right? Get added. That's why this equation holds good. A1 V1 is equal to A2 V2, and then unit wise, if you look at, this is in meter square cross sectional area, whereas velocity is in meter per second, so it will come meter cube per second as the discharge. Okay, next equation that we have is conservation of conservation of energy principle. The total energy at section A here is equal to total energy at section B. Of course, there is an assumption behind this that the fluid is ideal fluid. With that assumption, we can state this. Otherwise, how to apply for real fluids we have seen. So this is nothing but Bernoulli's equation, which we have studied in the last class with application in some cases of numerical problems also. So conservation of mass principle, that is continuity equation. No flow can just come or disappear, right? No matter can just like that cannot come, and then just like that cannot disappear. That is what is conservation of mass, which principle of conservation of mass comes in the form of continuity equation. Conservation of energy principle comes in the form of Bernoulli's equation. Total energy at A equal to total energy B. How we write total energy? You know that there are three parts in it. There is a pressure head, P by gamma. There is a velocity head, V squared by 2Z. Plus there is Z or Z, which is elevation head or datum head it is called. So that way total at A should be equal to total at B. This you have already seen. Now there is an impulse momentum principle. How it is different from the other two is, this is a vector equation. Impulse is nothing but product of force and time. You know this equation, F equal to ma, only the format is different here. So we know F is equal to m into A, everyone knows, right? but acceleration is nothing but rate of change of velocity. So because of that, what we can write here is this is m, and then final velocity minus initial velocity, that is v minus u, divided by, we have time. This is time rate change of velocity. Now this t we have taken on the left hand side and straight away written as ft equal to mv minus mu, right? So right, so there is a pressure force, there is external Rx force, the same angle theta we are talking about, the component of the force P2A2 cos theta acts leftwards. So this flow V1 with the velocity V1, it gets in, with velocity V2 it goes out, satisfying the condition A1 V1 equal to A2 V2. But if you take that velocity and resolve it into components, you can just see here I have put it parallel to the original direction. So this is V2, same thing with the same angle, so angle is not differing. So because of that, this component is V2 cos theta, this is V2 sin theta. Then okay, Ry is the force in y direction, and P2 A2 sin theta is the component of pressure force coming downwards. So Rx and Ry indicate forces on bends, as just now shown. This resultant force R will be acting on the bend, right? Or bend will be putting a force on fluid. So basic equation is sigma F, or total force F, equal to mass rate of flow multiplied by change in velocity. So just now we have seen that there is a P1A1 in x direction minus Rx minus this P2A2 cos theta. So all x direction forces is equal to mass rate of flow is rho into q. Then change in velocity, that is final velocity. Now we are talking in x direction, right? So final velocity is over here, v2 cos theta, means after the bend the velocity in x direction if you talk about. So this component comes here, v2 cos theta. The original velocity was v1, so minus v1. So if you rewrite this equation for Rx, taking Rx on the other side, you will have P1A1 minus P2A2 cos theta minus rho q V2 cos theta minus V1. It is original format is this itself, right? But put in terms of all these pressures and velocities. Okay. Now if we apply the same equation in y direction, so what are the forces? There is upward force of Ry minus the downward forces of P2A2 sin theta equal to mass rate of flow does not change, rho into q, m by t is rho into q. Change in final velocity, so you can just see here after the section the flow will be going upwards with v2 sin theta, that is there, minus in the beginning there is no velocity in this direction, it is 0, so that's why minus 0. So applied in y direction. Again if we simplify for Ry, it will be equal to P2 A2 sin theta plus rho q V2 sin theta. So these are the two expressions we will be using in number of numerical problems. Okay. So these are the equations, Rx equal to and Ry equal to. Okay. So I have kept the equations over here. Let us see a numerical problem situation. There is a right right angle bend, and as seen here in the data, cross sectional area is pi d squared by 4, and it looks there is no change in diameter of the pipe. So that's why it is A1 is equal to A2 equal to 0.0314. The discharge through this is given Q equal to 0.15 meter cube per second. So what happens is we can find out the velocity using continuity equation. So Q equal to A1 V1 or AV, if I write, I'll be able to get velocity, and velocity is remaining the same as the diameter is not changing, 4.78 meter per second. Now what is flowing? There is a liquid with density, with specific gravity 0.8. So if we calculate rho of that, it will be 0.8 into 1000. So it will be 800 kg per meter cube would be the density. Now the pressure P1, they might have given that it is 0.5 meters. The data might be P1 or the pressure head in terms of, it will be gamma H, right? This this pressure head is given to be 0.5 meters. So what happens here is P1 is equal to, this is gamma, this portion is gamma, because gamma is substituted, you know that already, it is specific gravity multiplied by gamma W. Specific gravity multiplied by gamma W, that's why it is 0.8 into 9.81, and this is nothing but H, that is pressure head, and this is nothing but gamma. That's how pressure is calculated. So this comes out to be 3.924 kilopascals, right? Now assuming that there is no pressure given here at point 2, I can apply always Bernoulli's equation, right? And we'll see that P1 and P2 are same, right? Because the velocity is not changing, and hardly there is any difference in elevation. Actually speaking, this is a horizontal bend. Because of that, the Z does not come into picture at all. So P1 is equal to P2. This is preliminary analysis. We have applied continuity equation. You can remember the steps. We have applied energy equation. Now we are going to apply these two equations, which are impulse momentum principle. Let's see how. So for this you need forces. So F1, or this force, which is P1A1, PA, if I calculate, pressure is 3.924 and cross sectional area is 0.0314. With that it becomes 0.123 kilonewton it becomes. Okay, now we'll apply the equation P1A1 minus P2A2 minus rho Q P2 cos theta minus V1, right, is equal to Rx. Now in x direction, this value P1A1 has become 0.123. It is in kilonewton. So this is one more information I want to give you. Better you use all newtons only rather than kilonewton, otherwise it will be a bit confusing, right? Anyway, here I have substituted because it is in kilonewtons. Okay, Rx minus Rx is in kilonewtons. I have put these things on this side. Rho is 0.8 into 10 raised to 3 into Q mass rate of, volume rate of flow 0.15. I have multiplied. Now if you look at this row, which is in kg per meter cube, okay, you have to understand in the beginning only these things. That's why this is kg per meter cube multiplied by Q is a meter cube per second. So it becomes kg per second. Okay, then you have here there is a multiplier of velocity. Okay, so multiplied by velocity is meter per second. Overall, what would be the units of this right hand term? This right hand term will have rho kg per meter cube, q meter cube per second into the velocity, because after plus or minus whatever it is, the overall units will be meter per second. Now if you look at this meter cube cancels with this, you will be left with kg meter per second squared, which is nothing but Newton. That's why I was telling you Newton has to be used. Now because I have used kilonewton on the left hand side, I have to convert this Newton into kilonewton. That's why this 10 raised to 3 I have divided to convert everything into kilonewton. Okay, now continuing, this is what this is, change in velocity, that is beginning v2 cos theta. Here the velocity is this way, so there is no component of velocity, or if you substitute 90, cos 90 is 0, right, minus v1, original velocity there is 4.78. okay, and the p2a2 cos theta, this is cos 90 again, because of that this is also 0, right, so this becomes 0. So that's why equation is like this, Rx equal to this much. Now if we apply Ry, P2A2 sine theta, now P2A2 is the same value, right, 0.123, but sine 90 is 1, because of that whole value acts. That's why this is 0.123 minus Ry going on the other side, and this I have taken the left hand side, because of that there is a negative sign. Rho into q is fine. Okay, of course you have to divide it by 10 raised to 3, that is there, 10 raised to 3, because we are using kilonewtons. The velocity is 4.78, right, v2 sine theta in the vertical direction we are talking about. So this is full value. Okay, then Ry becomes 0.697. Now you have to find out resultant of these two. So that is the first problem. I don't know how much you have understood. Hope in this problem everything will be more clear, right? We'll go for this. This is a problem from question paper, right? What is given is the discharge is given 250 liter per second, but we want in meter cube per second. I have converted 0.25 meter cube per second. It is said that it is water, because of that gamma W can be used. That's why they give this, so you should be careful. The diameter of the pipe is 0.3. They have not mentioned whether it is changing or not, so obviously everywhere the diameter is remaining the same. The deflection angle here, originally it was going this way, right, original flow was this way. Now it has changed its direction and going this way. That's why it is 135. R and alpha means what is the it is force on the bend or off the bend on the fluid and its direction. The pressure is equal to 39.24 into 10 raised to 10 raised to 4 Newton per meter square. It is mentioned. Okay, all this is a data now. Now area, if I calculate with the diameter D, right? So this comes out to be 0.0707 meter square. Now I can calculate P1A1. So P1 is there here, P1A1, and there is no change in diameter. Because of that, A1 is A2. Pressure is also not changing because there is no change in velocity. So P1A1 and P2A2 comes out to be 27,737.122 newtons. Now Q equal to A1V1, which is 0.25. Rho is 1000 kg per meter cube. Now velocity from this equation becomes V1 equal to V2 because there is no change in diameter, 3.537 meter per second. Okay. Now these are the equations to be applied. Let us see how it will be. Okay. Now here I have used deliberately Newton units, so you have to make a clear idea that use the units of newtons only, right? If I want to write full, I have to write it this way, newtons. Okay. Now P1A1 I have calculated. I'll substitute. P2A2 is also same, because of that it is taken common. 1 minus cos 135 minus Rx. Here it is Rx. Rx and Ry is equal to rho, that is 1000. Q is 0.25 given. This velocity, again it is remaining the same, V1 equal to V2. That's why 3.537 is taken common. Inside you got cos 135 minus 1. Okay. Now why I have not divided by 10 raised to 3? Obviously because we have taken in newtons. There is no need of converting Newton into kilonewton. That's why that division. In earlier problem I divided by 10 raised to 3 only because it was in kilonewtons, right? We wanted to convert that into kilonewton rather. Okay. From this, if you simplify, Rx comes out to be equal to 48,859 or 48.86 kilonewtons. Now Ry minus, if we apply this equation, P2A2 sin theta comes leftwards, so Ry minus 27,737.12 into sin 35, okay, that is the equation, is equal to rho into Q, rho into Q. Because it is water, it is 10 raised to 3 rho, right? It is said that it is water, rho, and this is Q. The order is changed slightly, take care. Rho into Q into V2 sin theta. V2 is the same velocity we have, sin 135. Now if you simplify, you're getting this value. Now to find out the resultant force, you can just see that Rx is leftwards 48.86 20.86. Ry, which is indicated like this, has come 20.24. So that is the force. Now resultant of these two will be inclined like that. I can find out R equal to square root of 48.86 squared plus 28.4 squared. That's how I have calculated R. Alpha can be found as tan alpha. Now if you apply tan alpha, which will be equal to 20.24 divided by 48. So it comes out to be 22.5 degrees. Now when we say that this is the force, whatever R that we have, this is nothing but force by the bend on the liquids. So force exerted by the bend on the water. Now if you want to find out what is the force exerted by the water on the bend, it will be exactly reverse, the same force, but this reverse manner. Force exerted by water on the bend will be the same R with the same inclination, but it is in this direction. Okay.